So we're going to talk about existence theorems, which, as the name suggests, they're theorems that help us prove the existence of a solution. They're not methods for how we're going to get there. Their purpose is just to let us know that, hey, you're going to find an answer. It's guaranteed to exist as long as you meet the initial conditions. All right? So we're going to start off with just reviewing a little bit of vocab. We're going to talk about a differentiable function. And the definition reads, a function f of x is differentiable if and only if f prime of c exists for every value of x equals c in its domain. Okay, so a function is differentiable, aka I can find its derivative, and I can say the derivative exists if and only if its derivative exists for every value in its domain. All right. Polynomials, sine, cosine, exponential functions are differentiable functions, meaning that if we take the derivative of a polynomial or a sine or a cosine or an exponential function, we can say those are differentiable because when we get those derivatives, we can plug in any number into in for x, whatever its domain is, and we're guaranteed to have an output, aka we're guaranteed to find a value for its derivative for any possible input. That's all the differentiable refers to. So we're going to talk about the intermediate value theorem. That's going to be the first existence theorem we're going to discuss. And it states, suppose that f of x is continuous on the closed interval a to b, and let m be any value between f of a and f of b. Then there exists a number c such that a is less than c, which is less than b, and f of c would equal m. So the best way to address this is to just take a look at the graph provided here, right? So here's what we got. Suppose that f of x is continuous on the closed interval from a to b. So that means that we have a function here, f of x. It is continuous because the limit from the left side and the limit from the right side exists, aka there are no holes or there aren't any vertical asymptotes, no weird behavior in this graph. It's just there. All right. It exists for all values, no jumps, nothing like that, just plain and simple. And let m be any value between f of a and f of b. So right now we have two things going on. We have the input dealing with the x value. So we have a and we have b, right? And there exists a number c. So we're talking about a c here, a c there, a c there. Like at least one of these is guaranteed to exist. And we're saying that that number has to be between a and b, right? But now they also introduce something else. They're saying let m be a value between f of a and f of b. So now if we look at the outputs of the function, we're saying that as long as we have a continuous function, right, between a certain closed interval, if we choose a number m that's somewhere between the outputs of the endpoints of the interval, at some point, this graph that we have, which I'm going to go over in the red, right? This graph here will have an output that is equal to m, like it has to equal this number twice because it's continuous, right? And we don't know where or how it's going to happen. We just know it has to happen. So I see a point right there, a point right here, a point right there. Those are at least one instance where f of c is equal to m. That's all the intermediate value theorem is saying, right? But if you want, we can do another like more concrete example. So let's say we have x squared. F of x is equal to x squared. Nice simple parabola. Let's say we have the closed interval. Let's see, -3 to 2. Okay, and I want to see where f of x. Well, okay, so first thing is I have a continuous function between a and b so far. I want m to be a value between f of a and f of b. So I need to figure out what f of -3 is 9, and what f of 2 is 4. Okay, so that means that my m value has to be something between these two numbers. So let's say that m equals 7. Okay, what this theorem guarantees is that if I have this graph right here, which is, oops, let's get the red, from -3, 9 to 2, 4, at some point where this is equal to, or my y value is 7, there should be an intersection, and I can see it occurs right here. And this number, right, if this is where -3 is, and this is where +2 is, oops, my input has to be somewhere in this range, and I've located it. It's going to be right here. And that's all the intermediate value theorem is stating. It's just, it has to exist. All right. So let me see if I can pull up this thing again so I can pause the video. Okay, so we're back and we're recording. All right. So that's what the intermediate value theorem is. And again, you just have to make sure that you meet the initial condition, right? Which states, and it's the first sentence, suppose there's a function f of x that's continuous, and you got to make sure the m value, the output, is between the two outputs of the endpoints in your interval that you were given. So just like how I did it, I wrote out the equation, had the interval, I had to test out the endpoints, and then I could say, well, this number is between it, so I know it should exist, and I verified it. That's all there is to it. So we also need to talk about Rolle's theorem. So I think Rolle's was a French guy because his first name is like Michel. Not Michael, Michel. So Rolle's theorem states this: let f be a continuous function on the closed interval a to b and differentiable on the open interval a to b. So the first thing you have to do is you got to make sure you're working with the right kind of equation. So I'm going to highlight the initial conditions that you have to verify. It's on the closed interval and it's differentiable on the open interval if f of a equals f of b, right? That's the other part you need to meet. As long as all of this highlighted stuff is true, this theorem applies. If it's not true, then the theorem does not apply and you cannot reach a conclusion. Easy as that. Okay? So let's try it out with the example we just had, right? I let f of x be x squared, and I had the interval -3 to 2. Okay? So I know f of x is continuous because it's a polynomial, and it's differentiable because, again, all polynomials are differentiable. So that first part, that of the initial conditions, is still true. I need to make sure f of a is equal to f of b. So f of a would be 9, and f of b would be 4. And I did not get the same number, so theorem does not apply. All right, if I don't know that the two values of the endpoints are the same, then I cannot use this theorem. And since they weren't, I'm done. I can't use it. Not happening. So let's modify it so that we can use it, so we can see what they want us to do, how this theorem works, though, all right? So I'm going to modify by changing the 2 to a 3. F of 3 would produce a 9, so f of a equals f of b. It's still true. What the theorem is stating is that there must be at least one number c, right? So somewhere in this interval, there should be a number c such that f of c would equal 0. Okay, so f of x is x squared, so f prime of x would equal 2x. And I want 2x to equal 0. Okay, well that means that x has to be 0. And if you notice, this number that I was looking for, this value of x, is in this interval. It was guaranteed to be in there according to Rolle's theorem. And I know this is kind of like a simple example, but I'm just trying to show you how to apply the theorem and how, like, why you just really have to make sure you meet the initial conditions before you do any kind of work with the derivative. Okay? All right, so that's all I have for you for this one. Hopefully it helps. And I'll try to end the video real quick, but my computer's being a little slow, and done.